I want the ring to be a nucleophile. And if the ring is a nucleophile, I want this ring, right? This ring is more nucleophilic, and hence it's more likely to undergo electrophilic aromatic substitution. This ring is a weaker nucleophile, and hence it's less likely to undergo electrophilic aromatic substitution. Today at some point I'm hoping we're going to get to nucleophilic aromatic substitution, and when we get there, the trend would be opposite. Does everyone understand what I mean? That it would be opposite. Because when we present a nucleophile to the ring, we're presenting it to a ring that has to behave as an electrophile. Okay? So electron withdrawing groups are good there. But the question was specifically asking about electrophilic to Kim, up here to Kim. Specifically asking about electrophilic aromatic substitution. Okay? Are there questions about this? Ask questions. You really need to ask questions. There is no dumb question. I'm not up here judging you. Yesterday, if you were in my office, I asked people what ILY meant. So you might think that's pretty stupid, right? I'm sure y'all do. But I asked because I didn't know. So there are no dumb questions.
Why is the dipole arrow going to that other benzene?
So in this case, my directly attached atom is like an R group. If I think, and look, very locally, this is like a toluene, right? So inductively, that group is pushing electron density into the ring because it's a donator of the inductive variety.
Oh, okay.
Okay? Are there other questions about this?
Would that carbon's inductive effect be neutralized by the other weak electron withdrawing?
No. No. Not a little bit, but not enough. So the question was, what is the product? The product should have been, truthfully, a BR being added to the para place, the para site. But it's also added to the ortho site. And it really is a 1 mole addition. Okay? If you have more questions about this, I'm happy to talk about it after the fact. Now, here's the kicker. On my 231 homework and on my 241 homework, you have the same structure for 2. Now, do you want to know how many students? Let's take a guess. I have 250 students in my 231 class. How many students from the IR that you were given for this molecule, okay, just the IR, how many students do you think in my 231 class were able to come up with this structure?
7.
50%.
You want to know? 200.
What?
Yes way. You know what they did? They looked it up online. Yep. That's crazy. I fight against this all the time. How can you learn if you go look it up online? You can't. Okay, this was the answer. You had the NMR, you were able to get through to this, right? Now, I don't care if the OCH3 is here, or here, or here, or here. I don't care. I don't see how you would be able to discern that because you didn't have the coupling, nor do you know how to deal with the couplings because we didn't teach you and we're not going to teach you. So the OCH3 could have been anywhere on here, okay? And I will follow through with your synthesis, okay? Now, there are definitely some issues with the synthesis, okay? So let's talk about one way that we can do this. This is not the only way. I'm trying to get around something, though, that you may lose a few points for on the exam. So if you can go without losing points, that would be better than going with losing points, okay? Some of you may have simply wanted to do something like this. Start with benzene, and then add, you could have made, say, something like this, okay? And then add that to benzene, right? So now you're at, or even had a Cl out here, right? You could have done something like this, and then tried to do that addition. Now, while that's going to get you there, okay, you are going to process through or proceed through a primary carbocation, which we know isn't really the way that we want to do that, okay? So that's probably not the best way, nor do you really know how to very efficiently make that molecule from propane, right? So that's another issue, okay? So one way to do this is to make this type of molecule, which is actually very easy to make, according to what you know, starting with propane. You can make this guy here. made into a Gilman reagent very easily and swapped out. So I can make this into a Gilman reagent, which would look like this. And I can add this now to something like a halogenated benzene, right? And swap them out, one for the other. Okay? Let's stop here. Whispering means that you have questions. So if you have questions, you can raise your hand. Because we all want to know what they are, honestly. So we're all going to learn. This is a great learning environment. Yes?
So isn't that left one just acylation?
This left one is acylation. The acylation here, this acylation is fine. What happens is if you go on from here, you're actually going to see a rearrangement, right? This is what, in essence, you get from that, something like that. You're going to see a rearrangement from that primary carbocation. Yeah?
Could you have Grignarded that?
Grignarded that. No. You can't Grignard anything that has a ketone, any acidic proton, or no carbonyls can be involved in a ketone, because Grignards react with ketones. We haven't gotten to that chapter, but they do, and you'll see they do. So you've got to stay away from all functionalities that are on there. Yeah?
Would it have been wrong to eliminate and get the alkene after you added?
No. I mean, there's many ways to do it. I'm purporting one way that you could do based on the reactions you know to date, right? That's always what I'm trying to do. You guys use the internet, but in essence, that internet's not going to help you on an exam, right? So I'm trying to get you to not use the internet and to actually use your brains. That's really what it is. Yeah?
Would you want us to show how we got to the actual Gilman reaction, the first part, or could we just go directly to CUI?
In essence, you were being asked that, but I'm probably, if you didn't understand that, I probably will not dock points for that sort of thing. Okay? All right. So let's proceed on then. Okay? If I then did something like H2 platinum and then NBS, I'm now going to get to this guy. And if I NBS this, I have a very different starting material to make my ring closure than that. Okay? This is really what I want you to compare. You can hand in your homework to Kim up here. If you do ALCL3 here, or ALBR3, or whatever you want to do, you're going to get something like this. Okay? That is the ring that you want, right? Hold on just a second, Mickey. That is the ring that you want. This isn't the ring that you want, because while I'm going to give you partial credit for doing this, for sure, I'm going to give you partial credit, okay? But this is something we need to understand about these reactions, because you could lose points in other areas of the exam if you don't remember that these intermediates rearrange, okay? That these intermediates rearrange, all right? So the problem is, this sees a rearrangement. You might get some of that 5-membered ring that you want, right? Total 5-membered. But this is going to get you your 5-membered ring. Mickey, what's your question? Yeah.
When you add the H2 platinum and NBS, how did you get another double bond?
Oh, did I not? I didn't do my, thank you. I didn't do my process through. Thank you. -1, Dr. Dixon. Yeah.
On the last couple of sentences so far,
Yeah.
how do you close the connection?
Okay, that's a great question. And Kim had this, Kim, I keep calling her Kim. Caitlin, are you here? Because I keep calling you Kim. I don't know why you look like a Caitlin, but you've been Kim all week. And everyone's like, who's Kim, Dr. Dixon? I'm like, oh, Caitlin. Okay, so
They
so
know
I
it's
meant
Kim.
like, you know, yeah, who did say that? That's actually a good point. See, I'm not always swift, I'm telling you. Okay. Yeah. So this is how this works. And Caitlin did something like this on the board. Okay, she initiated this sort of concept on the left board. But this is how this works. If I do now this with ALCL3, my first step is to attack the aluminum, right? The halogen attacks the aluminum center. The nucleophile is the halogen. The electrophilic center is this group 3 atom. We know these as The aluminum now has 4 bonds. The Br in essence is given away an electron to make that bond. So the Br is positive and the aluminum is negative. Okay? What actually happens here then is this bond between the Br that's positive and the neighboring carbon is relinquished toward the Br, because the Br wants an electron pair back, right? That's what's going to satisfy Br, right? It's going to make it neutral now. What it's going to leave behind, though, is that carbocation, which we know is resonance stabilized, okay? Hence, you're going to get something like this as an ionic association, okay? And it's this positive charge that's my electrophile for my nucleophilic reaction here to that electrophilic center. And that's what closes the ring. You can't hear. I've been told to repeat questions. Sometimes I'll repeat comments. That comment was, what? That was a good one. Yes?
What's the likelihood of rearrangement there?
The likelihood of rearrangement is somewhat, for sure, but it's not enough because you aren't going to be able to really get a 3-membered ring compared to the 5-membered ring that can result, right? That's why also, while this is likely your major product, you are going to get some 5-membered rings, right? Because 5-membered ring is more stable than the 4-membered rearranged ring that you can get, right? But a 3-membered ring is never going to win out over the 5-membered ring, right? So that will definitely happen, okay? Yeah.
Does that say NBS, comma D for 2?
That says MBS, comma, triangle.
Oh,
and triangle is
triangle.
heat. Yes.
Okay.
Everyone see where she's asking? This says MBS, comma, triangle, which is heat. Not MBS, comma, D for Dixon. Right? Guess I am in rare form too. I don't know what has happened to me the last day. Okay. Actually, I do. It's a very funny story. I'll digress right now. So my daughter went to high school yesterday, and we constantly tell our kids not to watch those stupid Disney programs, or even some of the sitcoms they have, because that just doesn't happen in real life. You know, like all those things don't happen in real life to one person, and no one has all those witty comebacks all the time, right? That's just not real life. So we're telling our kids this all the time. So my daughter, of course, goes to high school yesterday, at which point someone threw a cigarette into a trash can. There was a fire. The sprinklers went off on one whole floor of the building. They left the building, got sopping wet, sat outside for 45 minutes.
Oh my God.
Then the wall collapsed. The power went out. Sat in the auditorium for an hour with no power. Then they all had to eat lunch in the cafeteria together. The whole blessed high school, and a massive food fight ensued. And soup were thrown around, entire buckets of soup. And that was, Dewey, where are you? That's Reservoir. Yup. Isn't that good? So she came home and she was like, you know how you tell me that life isn't really like a sitcom? You're wrong. Well, I'm in rare form after all that. Okay. All joking aside, yeah.
Do you always need heat with MBS?
You always need heat with MBS. I have not docked anyone on that, nor will I start to dock people on that, but yes, heat is necessary. Okay, does everyone see how I got a 5-membered ring?
Yeah.
Okay, yes.
You created a carbocation.
I created a carbocation that is primary, but it's primary and allylic. So this is like equal to a better than a secondary carbocation. So this guy is good. That carbocation, which I would have created over here. So let's look at the carbocation from over here. Everybody turn their head to the left board. And everybody on the left board, show me the mechanism of this with AlCl3.
Yes,
Go. Good exam level question. 2 minutes on the clock. I'm counting. Can you show me the mechanism of this with AlCl3 to give me this product? Okay? 2 minutes on the clock. This is exact exam question. This could be an exact exam question. I've seen this on my exams before.
Glad.
I'm going to compete with you here. So this is exactly what you should have gotten. Okay, I'm going to walk you through this. It's almost identical to what's going on here, right? It's the same process of thinking. You know the thinking process. You can do this for anything that's on an exam, okay? The first step is the attack of the CL at the aluminum center, right? That's the first step in any of these Friedel crafts, acylation or alkylations. This gives me this intermediate. Just like over there, the aluminum takes on a negative charge and the Cl takes on a positive charge. I lose the bond between the Cl that's positive and its neighboring carbon. It comes back toward the Cl, leaving me with a carbocation center that in this case is primary, right? So we see the hydride shift to the secondary and then the attack of the pi bond in the ring onto that secondary carbocation, okay? To lead to this product here, okay? This is a very typical mechanism. All right, are there still questions about how we're using aluminum trichloride? Yeah?
Just, it's a different question. Can you have a Gilman reagent with a Cl at the end?
No.
Yes. You like the cat.
Why did you say there would be no hydride shift over there?
Okay, so there's no hydride shift here because it would lead to a vinylic, right, carbocation. So there's no hydride shift. There is resonance, but the resonance isn't going to happen because you create a three-membered ring. Work through that, and that's really unstable. Yeah.
I'm guessing it's the double bond that helps connect to the carbocation, right?
It's the double bond that makes this carbocation stable that allows the five-membered ring to form. Yeah.
But it's still going to be
Yes. Okay. Yes.
When you undergo installation, do you need water at the second step?
You need water in the second step. Generally, as a cleanup, we generally don't talk about those, although these questions come up again and again and again. When the reaction's done, you have to clean it up. There's some acid there, there's some ions there. So generally what you do is you are adding water as like a, what do they call those, workup steps in your laboratory environment. You would need to do that, right? So you dump some water in, you shake it up in a set funnel, you take out the organic layer, that's what you want, right? And then all the ions and acids sort of flow into the aqueous layer. So it does clean up what you want, yes. Okay, yes?
Is there a double bond where the rings meet at the end of the product?
Is there a double bond? No, there's no double bond in here.
Like
And the benzene.
so like
Oh, here, yes, there was benzene and it came to this, yes. Okay, so once you're here, I hope that you can make the ketone there, right? H2OH plus would get me an alcohol, and then I can use PCC or something like that, right? So H2OH plus and something like PCC is going to get me now what I want, okay? I don't want to use KMNO4. No KMNO4. Why don't I want to use KMNO4? They're going to give me benzoic acid, right? Don't do that. Okay, so now I'm at this, and the next thing you need to do is add OCH3 onto the ring. There'd be a faster way to do this once we go through the nucleophilic aromatic substitution. If you looked ahead, I'm okay with that. I'll take it. But based on what you know already, you probably would have needed to do sulfonation, right? A little bit of acid base to make that an alcohol, and then do a Williamson ether synthesis. So something like sodium metal followed by CH3Br. I will write out, if you want to see very quickly, what these look like after each one of these steps. Okay? So after step one, I'm going to get this guy here. That's step one. Is everyone with me over here? Okay? That's sulfonation. Now I'm making it phenol. I'm going to cheat. Now it's phenol, right? An OH. That's 2,3. Now I'm using sodium metal. That's a GenChem reaction, right? It creates H2 gas and a negative charge here. So now I have phenoxide. And now I do CH3Br, and that is where I get to my final product. Because this is my nucleophile that's going to attack at CH3Br in an SN2 reaction and give me my methoxy group. Okay? Now, I am sure that this synthesis threw you for an absolute loop. Okay? And I'm okay with that on a homework. I'm not okay with that on an exam. So note the synthesis will be much easier on an exam. They're not going to be easy if you don't know your reactions. So sometimes getting you to do the harder syntheses on homework allows you to really talk about the reactions more and learn them better so that you can come into an exam. So there are some tricks in here that I want you to note. I'll get you in just a second. There are some tricks in here that I want you to note. One is the use of a Gilman as the R, yep. Two is understanding these intramolecular reactions, right? And how to capitalize on the least amount of sort of byproducts you can create. Getting the major product to a major extent, right? So this concept, right, gets you through to that. The Williamson ether synthesis is always very useful in the end. Now there's some questions that came up with that. Yeah?
I just had a quick question. Are you allowed to do H plus and then 3 OCH3? Like, I was just wondering how like that would work. The OH I know adds in for the
No. Instead of OH minus OCH3.
No.
Actually, you know what? I think that would work. I think it actually does work. I'll give credit for that. Yes, I believe it does.
Can you explain what the Na metal does?
The Na metal actually deprotonates any alcohol, right? That's what it does. Water or any alcohol is literally forming its conjugate base by Na metal. And H2 gas is formed and it goes off. You ever see like metals, they light on fire? Yeah, that's why. Yeah,
How do you know that the ketone will be made on the right side rather than...
Because the carbocation that forms is going to be preferred to be benzylic than secondary. Okay. Yes?
Carbonyl first, isn't it a meta director?
If I put in a carbonyl first, it makes that a meta director. This side would be, so in essence you're saying that this side is a meta director and this side is a para director, which is why it directs in here. Yes. Yeah. What if they're different? Then you probably are going to get a mixture of products. So if you started with, say, something like this, and you just had the ring at this point, you try to direct, right? This is going to go all over the place, all over the map. But you could probably potentially get out what you want. Yeah.
I'm kind of confused as to why KMNO4 would give you benzoic acid as opposed to PCC.
KMNO4 is always going to oxidize any neighboring benzylic carbons that have hydrogens, right? It's one of the things to watch out for. It's one of the tricks that you see as a trick, but it's not a real trick because we're telling you to watch out for it.
Why doesn't PCC do that?
PCC doesn't do that because PCC doesn't have the same oxidative prowess, right? There's a whole, you don't learn about redox chemistry really till Chem 2, right? But there's a whole sort of leveling of oxidizing agents. KMNO4 is sort of like off the chart because of its oxidation number, but PCC is not. Sort of a modified oxidizing agent. PCC is always useful. I would almost always use that.
Okay.
Yeah.
Isn't PCC more than one carbon, or is it allowed? PCC?
It is probably more than one carbon. Yeah. Okay. That's a good catch. Okay. That's following the letter of the law. I love that. Okay. Let's move on to question 3. This is a little bit long for an exam level problem, but it's definitely something you need to be able to do on the exam. Okay? So, problem 3 is all of these bases, right? It's asking you to put them most stable to least stable, or acids most, it doesn't matter, it's the same sort of thing. So my turning point is pyridine itself. That's always in the middle, right? So things that I know are going to be more stable, or make that base more stable, are electron withdrawing groups. I I know electron withdrawing groups that are resonance will do this to a greater extent than things that are induction. So I'm going to take a scan around, and I see I have a nitro group that's ortho, and I have a Cl that's ortho. Those are my only two electron withdrawing groups. Okay? So they were E and C. So here is C, and here is E. This is, I randomly put them up here. This is the right order though, because one of them is a resonance withdrawing group, right? Here is a resonance withdrawing group. Okay? And a resonance withdrawing group absolutely is going to have the greatest effect on acidity. Now, in terms of sort of a general number line here, you do something like this. Where here is my turning point, which is always the non-substituted version of whatever we're looking at. Okay? My electron withdrawing groups are always going to be down here. So this is going to be decreasing stability of the conjugate base, or increasing number for the pKa of the acid, whichever way you want to say that, because a stronger base, which means less stable, is going to come from a weaker acid, which is going to have a higher number for its pKa. Okay? So down here are my electron withdrawing groups. My resonance effects are the most. My inductive effects also make it more acidic, but not as great. I think about the placement of these, okay? The placement of these is that an OP placement is going to have a larger effect than a meta. So OP guys will always be larger than meta. The larger electron withdrawing effect means that it's going to be the most stable and derived from the strongest acid. Yes?
Why does the OP have a larger resonance effect if the electron pair is on the nitrogen? Shouldn't it be to meta?
Okay, that's a great question. So let's look. What makes this a better base, a stronger base? What makes it a stronger base is if I know, right, that this is going to become negative. The more negative that nitrogen becomes, the less stable, the more reactive that nitrogen is to give away its electron pair, right? Follow that with me here, right here. The more negative that nitrogen is, the more likely that is to behave as a base. My best bases have an electron pair and a negative charge. So if I can make that more negative, that's absolutely going to have the largest effect. Okay? Now watch what happens when I stick a nitro group on here. The nitro group actually pulls electron density toward itself, right? So, what I see is something like this. My first resonance structure on this guy is this one here. Okay? That's my first resonance structure. I'm not going to draw the others, but you know that they hop every other. Hopefully you've done enough resonance that you realize this pi bond will shift here, and this positive charge then shifts here, right? They sort of swap places. So where else is my positive charge? I'm going to track it on my original guy. My positive charge is here, my positive charge is here, and my positive charge is here. Right? Is that a good base? The answer is no, right? It's not a good base. And that's what this axis is about, right? You can think of this base as reactive it is, right? Because we always parallel words. We say stable, non-reactive. What's the other word I use? Stable, non-reactive? You know what I mean. Hopefully you know what I mean. And I can say unstable, more reactive, right? So more reactive, a negative charge out there, more reactive, right? It's going to be less stable. But if I get a positive charge out there, right, it's not behaving as a base, right? So it's got to be derived here from these stronger acids. Yes?
So for pyridine, is there any directing effect with the nitrogen instead of the carbon when you're adding a substituent to a ring? I know it's kind of off topic.
Yes,
but
there are directing effects on pyridine, absolutely. We can talk about that. It's a separate question. Yes, there are directing effects on pyridine. You would tackle that problem just like you would attack problem 4 from our homework. Okay? Yeah.
So, just to clarify, just if it's meta, like the nitro group is meta, then it makes it a really poor, like reactive. It's more reactive than this.
It's more reactive, but certainly it's not going to be above, right? But it's going to be more reactive because the resonance will never put the positive charge on that nitrogen. Okay? It's all thinking about stability or reactivity, right? Those are like sort of things that have to go hand in hand here. Okay, so this is my effects with resonance. If I'm considering my inductive effects are going to be such that the ortho is going to have a larger extent than the meta and then the para. So in terms of acidity, I have my OP resonance at the most acidic, my meta resonance next up in the line, right, in my continuum, my ortho substituted withdrawing groups, then my meta, and my para is closest in pKa or stability to my turning point, my base molecule, no substitutions. I come out here, and this is the mirror image. I have electron donating groups. My resonance effects are the largest effects, but they're going to be the largest destabilizing effects. The largest destabilizing effects. Okay? So I have my OP here and my meta here. My induction is going to be less of an effect, and what I'm going to see is PMO. Ortho is going to make it the least acidic, or the least stable, okay, depending on how you read your access. This base chart always works, okay? There's some issue in the theory in here, which we can talk about, and maybe we will talk about in terms of the clicker question on Monday, but that's a very directed question that's directing you to think just about that and to reason it out. And all I'm looking for there is a thinking answer. Not necessarily the absolute right answer, a thinking answer. One that shows you're thinking through the problem. I need you to think, guys. You're my future. I'm going to be 90 and you're going to be 40. Well, that's probably an exaggeration, but you know what I mean. You're going to be in your prime and I'm going to be counting on you. Okay? All right, so in terms of donating groups, I had a whole bunch of donating groups. I had methyls on here, and then I had NH2s on here. So following along here, my ortho methyl group, right, will be out here. My meta methyl group will be in here. And then, doesn't matter if it's there or not. And then my resonance effects. My resonance effects are going to be less weak when it's meta-placed and stronger when it's placed in the para position, okay? So if we kept going with letters, we would have been D, and this guy is meta, is this, see, I can't even match. A, and this guy is B, this one is G, and this one is F.
You got it.
So there you go. C, D, A, D, G, F. How we do? We did good? All right. Can you draw for me, 2 minutes, a resonance structure for this guy that explains why it is the least stable, most reactive base? Draw me or explain to me why this guy is the least stable, most reactive base. Can you speak those words back to me in a written language, obviously? Here is the pertinent resonance structure. There's a bunch that you can draw. This is one of them, and this is doing exactly what I said. It's putting a negative charge on that nitrogen. A negative charge on that nitrogen makes this a very reactive base. An unstable, reactive base. Hence, it's placed all the way to the right in our stability here. Okay? Are there questions about this? Yeah? Yes, I can. In repeat, a negative charge on that nitrogen in pyridine makes that the most reactive base, right? And the least stable, because the most reactive is the least stable. Those go hand in hand. They're synonymous. It's the most reactive because it's got an electron pair and a negative charge. It's gunning to behave as a base, okay? And that explains why it's so far over in our stability series. Yes?
Can we say that it's already kind of partially negative because of the lone pair that it has on it, or should we not say
No,
that?
you don't say that. The question is, do I say that it already is partially negative because of the lone pair? No. It's currently neutral. Anything that can make it more negative, that's going to make it less stable. And anything that makes it more positive is, in essence, decreasing its ability to behave in a basic capacity. Yes? One more time? Oh, I guess it had those, sorry. These in it. What? So I will likely take any swapping of A and B. I will. And there's a reason for that. I'm not going into it today. We will on Monday, though, go into that. That doesn't mean class is over, because I still have problem 4. Itching to get out of here, right? Damn organic chemistry. Okay, so problem 4 is this.
I'm gonna go. I even just that A and B though. I can't even be that. I was so frustrated. I was like, I did not figure out what this was. Which one? It's because the first one was right. So what happens is that you put a negative charge on the nitrogen, which is already a negatively charged molecule, so it makes it more reactive. It's going to want to give away electrons for
Okay, so this question was saying, show the mechanism. And where is it likely to add?
1.
Okay, it's going to add, this was C1, this was C1. 1, 2? Yes? Okay, great. It's going to add to 1. Now let's see if you can get the Y.
Resonance.
Yeah? Okay, it is definitely more resonance. Good, good. But how many resonance structures?
2.
2. There are 2 resonance structures here.
I got like 6.
and only 2.
You don't want to break apart the benzene.
There are no resonance structures over there.
And not aromatics or not
Now, why is that?
You don't want to break the aromaticity of the benzene.
Because you do not want to break the aromaticity. Okay? This here is an aromatic group. And if you begin to do this, ready? I'm about to do this. I'm about to draw a bad resonance structure. Here it is in all of its glory. This ring here is not aromatic. Not aromatic. Now I'm going to take a leap of faith here, and you're going to explain something else to me. Okay? We have to agree that this is not aromatic. So I'm going to go, and I'm going to remind you that when we were talking toward the beginning of the semester, and we were talking about benzylic and allylic carbocations, of which here is a primary allylic, and here is a primary benzylic, okay? No one questioned me as to why these were equal. You know the answer to that now. You know the answer to why a primary allylic and primary benzylic are equatable. I never said that the benzylic primary was more stable than a primary allylic, right? I've always equated them. No one's ever, you just don't want to question the teacher. Yeah? Don't question authority. Buck authority at every turn. Go.
You said buck, right?
I'm so happy to, whatever it is. I'm so happy to debate. Healthy debate is good.
You ask us why?
So why is that equal?
Why is it?
We should sync that. Wait, do you want us to use words?
The answer's right on the board. All right. We'll do nucleophilic aromatic substitution on Monday. Have a great weekend. And I remind you, challenge authority. Be good, learning individuals.
Wait, do you want us to like write words for that answer? I'm confused. You can